Hi everyone, welcome to this Math 111 video. We're talking about section 2.2 today, which is logarithmic functions. There are lots of rules for logarithms, just like there are lots of rules for exponentials. But that's in section 2.3, so I'm not going to talk about that yet. What I am going to talk about is the relationship between exponential and logarithmic functions. And that relationship is one we've seen before. A logarithm is the inverse function of an exponential. What that means is a logarithm takes the output of an exponential back to the input. Now, let me give you an example of that. I know that 3 squared equals 9. The exponential takes the squared as my input, applies it to the 3, and gives me the output 9. And a logarithm takes that 9 and runs it back through to give me the original input. They both work off base 3 in this example. Let me do another one. 7 cubed equals 343. That means that the 3, which is the power, that's the input, goes through my exponential with base 7 and comes out at the output 343. And the logarithm takes that 343 and sends it right back to where it started, to the number 3. This equation, 3 squared equals 9, shows me both the exponential relationship and the logarithm relationship. But we do have our own notation for logarithm. And to get there, I want you to practice using the verbal representation. So let me give you an example. Here is 3 squared equals 9. Now, if I were to say that in words, I would say that 2 is the power, because there it is. 2 is the power that goes on 3 to equal 9, right there. The logarithm takes that 9 and sends it back to 2. So if I were to write this sentence in words, I'm going to have to do a little bit of matching. The word is, we write as an equal sign. A logarithm is a power. So whenever I see 2 is the power, I'm going to think 2 is the logarithm. I write that log. It goes on 3, so I'll write the little 3 down here so I understand what the base is, to equal 9. And now I have written that exponential 3 squared equals 9 as a logarithm. 2 equals log base 3 of 9. Let's try it again. I had 7 cubed equals 343. That means 3 is the power that goes on 7 to equal 343. The ability to say this expression in this manner makes changing to a logarithm so much easier. Because I know that 3 is, so I'll use the equal sign. Whenever I see the power, I'm going to think log. It goes on 7, so I put 7 here in the base to equal 343. A logarithm is a power. 3 is the power. 3 is also the logarithm. So a logarithm is a power. If you can remember that, it really helps keep track of logarithms and exponentials. Okay, I've got some more paper. I'm ready to keep going. So let's just do one more. It's always worth it. Let's try some funky bases and funky powers. Let's look at 1/3 to the fourth. Well, that's 1/3 times 1/3 times 1/3 times 1/3, and which is 1/81. So that means that 4 is the power that goes on 1/3 to equal 1/81. And so I can build that as a logarithm. 4 is the power I write with log. It goes on 1/3 and it gives me 1/81. We can build logarithms with fractions. There's nothing wrong with that. How about 7 to the minus 2? Well, that's like 1/7 times 1/7. So that actually equals 49, 1/49. And now I have a negative power. -2 is the power that goes on 7 to give 1/49. So I can write that as a logarithm. -2 is the power. I use log for the power. It goes on 7 to give 1/49. How about an actual exponential function, 5 to the x? And let's suppose that 5 to the x is 625. Well, I can still write it as a sentence because now x is the power that goes on 5 to equal 625. So I can write that as a logarithm. X is the power that goes on 5 to get 625. Let's solve that with a table, actually. I think that's a good idea. We're going to use x and 5 to the x as our functions. Start with 0. 5 to the 0 is 1. No matter what, any base raised to the 0 power is 1. If x is 1, 5 to the first is 5. 2, that gives me 25. 3, 125. And 4, 625. There it is. X is the power that goes on 5 to give me 625, so that must mean that 4 is the power that goes on 5 to give me 625. X equals 4. The right side are my outputs, the left side are my powers. A logarithm takes the output and goes back to the power. This table contains both the exponential function working forward, left to right, and the logarithm function working right to left, working backward. Let's do, just for fun, I want to do another table. This time we're going to do x and 7 to the x. And 0 is definitely gives me 1. And if x is 1, I get 7. If x is minus 1, I'm going to get 1 over 7. And if x is minus 2, I'm going to get 1 over 49. And there it is. Minus 2 is the power that goes on 7 to give me 1 over 49, which is exactly what I got when I wrote it in words up here. All right, we've talked about, excuse me, formulas, words, numbers. Let's talk about graphs. In our inverse function section, when we had the graph of a function, like y equals 2 to the x, or how about f of x equals 2 to the x? Well, 2 to the 0 is 1, and 2 to the first is 2, and 2 squared is 4, and 2 to the fourth is 8. You see how quickly this blows up? And that's when the base is pretty small. Blows up really fast. And then 2 to the minus 1 is 1/2, and 2 to the minus 2 is 1/4. And so it shrinks down pretty quickly, but it's never going to get to the 0, because no matter what, I'm multiplying or dividing 2 by itself. If you multiply positive numbers, you can only get positive numbers. So I could say, what's f of 1? And that's 2. And in our inverse functions, we can use the same graph, f inverse of 8. So I go up here and I find the 8, which is way up at the top, and I come back down and I see that it's 3. The f inverse is a logarithm function, so 3 is the power that goes on 2 to give me 8. You can use the exponential function to answer logarithm questions, but logarithms are such important functions that we normally draw a logarithm function on its own. And when we draw a logarithm function on its own, we have to think about what the points are. And so to do that, I'm going to make a table here. Let's do the logarithm base 2. Oh, sorry, let's do 2 to the x as our table, because I find it easier to make exponential tables and then just work back from my logarithm. So I could have x is 0, 1, 2. So 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 3, and 8. So if I'm working with my logarithm, these become my inputs and these become my outputs. So my input of 1 gives me an output of 0. So I have that point right there. The input is 1, the output is 0. If the input is 2, the output is 1, which is there. If the input is 4, the output is 2. If the input is 8, the output is 3. And so I get something, and actually it starts off looking a little bit like a square root function, but it's not quite. It actually grows more slowly than a square root function. And the other thing is it also keeps going, because if I put in -1 as my power, I get 1/2 as the output, which means if I put 1/2 in to my function and I come this way, I get -1 as an output, and it actually goes down like this forever. So this is my log base 2 function. It always crosses at the point 1, 0, and it never reaches the y-axis. And then it goes out forever. It keeps going up, but it tries as hard as it can to flatten out. It just can't quite flatten out all the way. All right, so we looked at the 4 representations of logarithm functions. And I could keep going with more examples, but the truth is, the most important thing is just to practice this. Practice writing and saying logarithms. Like 7 to the minus 2 is 1 over 49, which means minus 2 is the power that goes on 7 to give 1 over 49, and writing that as a logarithm. Understand that if you want to build a logarithm table, you can just build an exponential table and work right to left and work backwards. And notice these x's are all the powers. So a logarithm is a power. And that is really where logarithms came from. They came from scientists working with really, really big numbers, numbers that grew by exponentially large amounts. And they realized, I can't keep track of all those numbers, but I can keep track of the powers. And they developed a logarithm so that they could keep track of the powers. And then be able to recognize a logarithm graph by these special characteristics. It always goes through the 0.10 unless you do some sort of funky transformations. It goes down along the y-axis but never touches, and it goes out to the right forever. So on your lab manual, you'll be asked for the domain and range of this function, and the graphical representation can really help with that. Okay, thanks for watching.